Today I'd like to share with you some visual observations and personal weather station data from northwestern Oregon during a wind and wildfire-associated smoke event. The beginning of September was clear and mild throughout the Oregon Cascades. However, drought conditions had the entire region much drier than normal. A few small fires were already burning, but several more began on the evening of September 7th. Historically, most large fires in the state have been in the more arid inland regions rather than the more densely populated river valleys. This outbreak of wildfires coincided with a strong windstorm out of the east, which itself was unusual for this time of year when the winds are more typically out of the west. As an example of how quickly and extensively these fires spread, one fire that had already been burning for 3 weeks grew more than 260-fold in the course of a single day, destroying several small towns. And these deadly fires burned a larger area of the Cascades than those of the past 36 years combined. The remainder of this presentation will focus on observations from the Portland metro area in the lower Willamette Valley, where the impacts were primarily smoke-related. Within this valley, the Tualatin River subbasin is separated from the Willamette by a 1,000-foot tall ridge. As this combined LiDAR and elevation map shows, the topography of the Tualatin Basin includes all sorts of nooks and crannies, which can influence water and airflow patterns. Data about this event was gathered using an ambient weather brand personal weather station near the southern edge of this ridge. These data include wind speeds, gust speeds, gust direction, and PM 2.5. A quick overview of the PM 2.5 unit of measurement. Particulate matter, abbreviated as PM, comes in a variety of shapes and sizes, including particulates less than 2.5 microns in diameter, which have the potential for being particularly biologically harmful. To measure this, a light sensor is used to count the number of particles in a given volume of air. This count is converted mathematically to a mass concentration using assumptions about average particle densities, etc. The resulting measurements are given in terms of micrograms per cubic meter. Conversion factor algorithms and equipment calibration can vary depending on the specifics of the type of sensor and anticipated source of pollutants. Many systems go on to generate an air quality index, or AQI number, from these measurements, but for the sake of this discussion, I will focus solely on PM 2.5 measurements and not AQI. So let's see what this event looked like from the point of view of a personal weather station at the northern tip of this smoke plume, which by September 10th was estimated to cover nearly 1 million square miles. The event began with 3 days of strong winds, including gusts between 20 and 30 miles per hour at our comparatively sheltered location. During this period, the air remained mostly clear while wildfire smoke was blowing out over the ocean. Looking at particulate matter concentrations, now shown on the y-axis where wind speeds had been, PM 2.5 readings began to spike as soon as the wind subsided and smoke moved into the valley. After a few more days, our particulate sensor became saturated and stopped transmitting data. Intermittent readings near that saturation point are shown in red. At this time, we brought the sensor indoors, where it remained for the better part of 3 days, with one attempt at replacing it outside on the 14th, when it immediately became oversaturated again. As you might imagine, throughout this event, other sources of air pollution data were also being consulted. I found no other ambient weather brand PM 2.5 sensors online to compare to, and noticed we were consistently seeing readings higher than either of the official DEQ sensors or those on the Purple Air network. However, within the Purple Air network, I noticed the site nearest us often had readings higher than the others in the area. Whether this difference was due to geography or calibration is hard to say, but it did inspire more detailed comparison. Recent studies have shown Purple Air brand sensors typically report higher particulate concentrations than regulatory monitors at same sites, which are carefully located, calibrated, and read by highly trained technicians. At any rate, let's start by looking at the DEQ sensors in the area. Of these mapped DEQ sensors, I was able to find data for 3. Through the middle of this smoke event, these sensors had a maximum daily reading with more than 200 micrograms per cubic meter difference between them. Most days, the easternmost site had the highest PM 2.5 readings, with differing geographic patterns at the beginning and end of the event, While no direct comparison between our home sensor and these official sites can be drawn, I was still curious about how much discrepancy there might be. As expected, our home PM2.5 sensor had readings higher than the official sources. But what about other residential stations? One station, just the other side of a small ridge from ours, was consulted most frequently, and it often had higher readings than the other sensors on the same network. Interestingly, that purple air sensor across the Willamette showed a daily maximum reading within the same range as the official DEQ sensors. Being curious about the impacts of small-scale geographic variability, I decided to compare data among additional sensors within the purple air network. Looking for more sites within this small but varied geographic area, there were a handful with data for this time period. Many more purple air stations have been added to the network since this event. By the end of the next month, the number of stations in this area had more than doubled. Of those with data available during the event, I further grouped them into 3 geographic areas, with elevations ranging between 10 and 250 meters. While not all of these sensors had data available for the entire period, they did provide interesting points of comparison. Early in the wind event, there was a little spike in particulate readings when a small amount of smoke blew in from Washington State. At this point in time, purple air and ambient sensors show similar readings. In the wee hours of September 9th, a slight increase in PM2.5 corresponded to a lull in the winds, and a more substantial increase followed after the end of the windstorm. While air pollution at this location wasn't particularly notable during the windstorm, the sky certainly provided a sense of foreboding. On the evening of September 8th, we were in a gap between smoke plumes, with thick smoke visible to the southwest. Through midday on September 9th, the smoke continued to build up offshore. Skies overhead remained clear, but smoke to the west was beginning to extend northward. A couple of hours later, mammothous clouds of smoke were flowing in from the west, and by early evening, the sky was a sea of orange and black. Throughout this period, air pollution levels remained moderate, but as they say, what goes up must come down, and when the wind subsided, the air pollution increased dramatically. As wind direction changed and the air became still, that massive smoke began to settle into the valleys between the Coast and Cascade mountain ranges. For the next 9 days, the mean PM2.5 for all sensors remained above 100 micrograms per cubic meter. By the following day, smoke extended inland beyond the Cascades Range. In looking at the data from the various residential particulate sensors, hints of a geographic pattern caught my eye. To highlight these, I've abbreviated the y-axis and will reiterate that this is merely observational data. That said, the 2 sensors in the southwest section, one of each brand, seem to run roughly parallel to one another, as did 2 west of the hills, and likewise those to the east. Unfortunately, the lower altitude center in the western cluster didn't have data for this time period. On the 3rd smoky day, a slight change in wind direction and air movement corresponded to a brief decrease in particulate readings, which then began to climb again once airflow ceased. That night, our PM2.5 sensor became saturated, and the purple air sensor nearest us showed readings of more than 200 micrograms per cubic meter, more than any of the others in the area. On September 13th, with our station offline, PM2.5 data was only available from the others, which continued to show highly variable concentrations. While there's not PM2.5 data from this location for the period, visual observations highlight just how thick the air was. On a typical day, the Coast Range is clearly visible. Take note of the tree in the neighboring park. That tree, which is not more than 200 feet from this vantage point, could not be seen at this point in time. After the worst of the winds, wildfires, and smoke, a mass of fresh air began to move in late morning on September 18th. At our residence, this one wind gust brought a great sigh of relief. For others, loved ones had been killed in these historic blazes. Containment efforts continued. Thousands of people were left homeless, and communities are continuing the long and arduous process of rebuilding in scorched terrain. But throughout the region, all had cleaner air to breathe. Thank you for taking the time to hear about these observations, and a special thanks to Stephen Bedrick for his help in making the wind plots.